Let's talk about maps. This wasn't exactly the kind of map I wanted to talk about, but it'll do for now. The defining characteristic of a map is its key-value structure. You can look up where something is by its key and then get whatever's stored at the value. This is actually pretty similar to our normal definition of a map. We can look up something by its name and then go to a location to get the value. For example, let's say I wanted to find Winston. I can look him up by his key or his name to figure out where he is and then go get him over here. Maps are also called dictionaries for a similar reason. If you think of a word as a key and the definition as a value, it's pretty much the same thing. Time to add another type of data structure to the mix. Before we dive into maps, I want to introduce one new concept quickly. A set is another one of these broad, abstract concepts. It's comparable to a list. It's also vaguely a collection of things, but with one big difference. A list has some kind of ordering for its elements. A set doesn't have that, but instead doesn't allow for repeated elements. You can think of a set kind of like a bag. You can reach in and pull something out, but you'll never know what order you're getting the elements out in. A map is a set-based data structure, kind of like an array is a list-based data structure. The keys in a map are a set. I know that's a lot of new terminology, but let's look at exactly what that means. The keys of a map, like the words in a dictionary, need to be unique. You can have several definitions for the same word stored in the value, but if you had the same word in the dictionary many times, you would randomly pick out a definition when you were first looking. Thus, each key only exists once in a map. And a group of these unique keys without any order is called a set. So what are maps useful for other than dictionaries? You can use a map for a lot of things that have unique names. For example, maybe you have a bunch of information about Udacity courses. You could store each course ID as a key and use that to look up more detailed information as values. Hi, I'm back again. Just wanted to stress the importance of the material you're about to learn. Using a data structure that employs a hash function allows you to do lookups in constant time. Let that sink in for a second. With everything you've learned so far, you need to do lookups in linear time. In a list or a set, you need to look through every element to find the one you're looking for. Stacks and queues let you look up the oldest or newest elements immediately, and priority queues will let you find the highest priority element quickly. But if you want any other element, you've got to do a linear time search. The ability to do constant time lookups will make almost any algorithm you write instantly faster. Okay, so how do these magic hash functions work? The purpose of a hash function is to transform some value into one that can be stored and retrieved easily. You give it some value, it converts the value based on some formula, and spits out a coded version of the value that's often the index in an array. Let's go through an example to clarify this process. Let's say you're running some big event. Maybe it's for people who like a certain type of music. Everybody who wants to come to the event needs to buy tickets in advance. All of those tickets are randomly numbered, and those numbers are embedded in barcodes on physical tickets that people hand you when they first arrive. You need to be able to look up ticket numbers fast when people check in at the event. Storing the ticket number in one of those incredible hash functions sounds pretty great to you. You have all of your numbers. Now you just need to come up with a hash function to convert them to hash values so they can be stored easily. One common pattern in hash functions is to take the last few digits of a big number, divide it by some consistent number, and using the remainder from that division to find a place to store that number in an array. In this case, the remainder turned directly into the index of an array. Why does this strategy work? Well, if the numbers we had assigned to each ticket were 0 to 100, we could easily store it all in an array and look them up instantly by the index. When numbers are big and random like the ones we started with, we need some way to convert those numbers into array indices quickly. That's how the constant time lookup works. You give your number to a hash function, which spits out a hash code that turns into the index of an array. You can go to your array and get your original value in constant time, since an array lookup with an index happens in constant time. Why use the last few digits of a big number? In most cases, the last few digits are the most random. If you were assigning your numbers in numerical order, the first few digits really wouldn't be random. They're more likely to start with a 1, a 2, a 3, etc. than later numbers like 7, 8, or 9. As it turns out, there's a flaw in our elegant system. There are times when a hash function will spit out the same hash value for two different inputs. This situation is termed a collision. There are two main ways to fix a collision. The first is to change the value in your hash function, or to change the hash function completely, so you have more than enough slots to store all of your potential values. You can also keep your original hash function, but change the structure of your array. Instead of storing one hash value in each slot, you can store some type of list that contains all values hashed at that spot. These lists are generally called buckets in this context. Rather than storing one value in each slot, you can store multiple values or a collection in each bucket. But are either of these approaches actually helpful? For the first one, you can maintain constant time lookup, but by using a bigger number in your hash function, you're going to require a lot more space to store your values. Also, if you do this reactively and change the value in your hash function every time you have a collision, moving all of your data to a new array is going to definitely increase the complexity in terms of both size and time. With the bucket approach, you still need to iterate through some collection, though a shorter one, every time you're looking for something. Hash functions have a constant lookup time in the average case, but because of the bucket system, you could end up storing every value in one bucket, and then you're still essentially just iterating through a list. In that worst case, this actually turns into big O of n. When done well, hashing is really fast and can save you a ton of time, but all of these things are very real concerns. There's no one perfect way to design a hash function. You need to consider all of these things and build a system that makes the most sense for your data and your limitations. Often you'll have to choose between making a hash function that spreads out your values nicely but uses a lot of space, and one that uses less buckets but might have to do some searching within each bucket. Ideally, you would have 1 to 3 elements stored in each bucket, so you can design a hash function with that in mind. You can also do something creative, like using a second hash function inside of a large bucket to split up those elements even more. That would work particularly well if you know you're going to have well spread out data, but end up having a few really large buckets. Hashing questions are popular because there's often not a perfect solution. You're expected to talk about the upsides and the downsides of whatever approach you choose to use. So just do your best to optimize your hash function and make sure you're communicating with your interviewer well. And finally, we reach the intersection of two very important topics: maps and hashing. Hash maps are one of the main places you'll see hash functions show up. In the previous example, we were just using a hash function to find a place to store keys. However, maps have keys and values. You can use the keys as inputs to a hash function, then store the key value pair in the bucket of the hash value produced by the function. Again, since you know the keys in a map are unique since they belong to a set, you could use a hash function to give them each their own unique buckets. You can also design a hash function to allow for collisions. In an interview, you'll often be asked to create a hash table to show that you understand hashing. Also, that you know the upsides and downsides of designing a hash function. However, hash maps are very useful to integrate into algorithms. Constant time lookups can really speed up your code. Keep it in mind and always think if it'll work first when thinking through data structures. The real beauty of this system is that you can use it with string keys too. You just need to come up with some hash function that converts letters into numbers. Individual letters can be pretty easily converted into ASCII values, and many languages already have functions built in that do that. We can combine the ASCII values with a formula to get a unique hash for each letter. So what should our hash function look like? Again, there are some trade-offs here. Do we want every word in its own bucket? Are you okay with collisions but want a relatively simple hash function? If you have 30 or less words, you can probably just use the ASCII value for the first letter of a string as a hash value. The standard hashcode function for string keys in Java favors a large hash table over having any collisions. The formula looks something like this. For example, let's say we're going to hash the word Udacity and we're starting with the first two letters of the string, UD. We can plug these ASCII values into the equation to get a hash value that is unique to our string. Why does this work? Well, by multiplying the ASCII value for each letter by a power of some number, like 31, we can guarantee that every number representation or hash value will be unique to that string. A hash function like that would be great for a dictionary where we need unique buckets for each string. However, strings with just 3 or 4 letters already have huge hash values. The trade-off is really important here. As long as you have the space for it, a unique hash value can be really useful. Lastly, why is the number 31 used here? The earliest hash functions took advantage of some properties of the number 31, and research showed that it was a great choice for this kind of string hashing. However, now there are more complex hash functions that have been discovered, so 31 is more of a convention than the best value for every situation. Remember that designing a solution for your keys is the most important thing. Don't get too bogged down in all of these conventions.
Sometimes, the people around us, whether they're our friends, colleagues, or family, try to give us career advice based on their own personal experience, and sometimes they give great advice. Other times, the advice they give, though well-intentioned, may not feel very supportive.
It's possible that at some point in your life, someone has told you that you weren't good enough at math, or that you didn't have the right credentials from the right university. Or you might have heard that it's too late to do what you want to do, or that you can't compete with all the other people out there who are aiming for the same job. I know I've heard things like this before. Lucky for us, the nature of work and education is changing. And we know from research that with well-applied effort, any of us can learn anything.
So, if you ever find yourself hearing comments like that, we'd like to remind you that you are learning from top industry experts and building industry-relevant projects. You have every reason to trust in your knowledge, skills, and ability to grow.
And as the great philosopher Taylor Swift once said, you can just shake it off. Shake it off.